Hello, this is Jack Jackson. In this video, we're going to begin looking at hypergeometric distributions. So this is continuing our look at a series of discrete probability distributions. In the past, we've looked at geometric distributions and binomial distributions. And the hypergeometric is similar to the binomial distribution with a little bit of a variation. We've actually looked at some examples of hypergeometric distributions earlier. So in this video, we're going to derive some of the formulas that we need for them and try to set the groundwork for what are the basic assumptions of a hypergeometric distribution. So first of all, let's compare and contrast a geometric and a binomial distribution. This is a review. So remember that a geometric distribution and a binomial distribution, in both cases, we do a series of independent Bernoulli trials. Remember, a Bernoulli trial is you just basically divide the sample space into two parts that you call one called a success and one called a failure. Once again, a success does not necessarily mean something that's good or bad. It just means that you got the thing you're counting. So anyway, the probability of a success each trial is P, the same probability each time. So they're independent Bernoulli trials with the same probability. And then in addition to that, the probability of failure, of course, then is Q, which is 1 minus P. Now, the difference in the geometric distribution and binomial distribution is, in a geometric distribution, we repeat these trials until we get our first success, and then we stop. So what we don't know is how many trials we're going to have, and that's going to be X. And then what we do know, though, is we're going to get one success, and of course that leaves X minus 1 failures before that. Binomial distribution is set up basically the same way, but here's the difference. In a binomial distribution, we know the number of independent trials ahead of time, so we're going to repeat in trials no matter what happens. But what we don't know is how many successes we're going to get. That's our random variable X. So let's review a binomial distribution. Suppose we have an urn with 10 balls in it. 6 of them are black and 4 are red. We randomly draw out one ball, note its color, replace it, and then draw a second, third, and fourth ball, replacing the ball each time. So this is selection with replacement. Let X be the number of black balls drawn. Make a tree diagram, formula, table, and graph of the PDF for this distribution. Well, notice that the probability of drawing a black ball, which is a success, let's see, there are 6 of them, and their total of 10 balls, the probability is 6/10, that's 0.6, or 3/5. So 0.6 is the probability of a success each time, and Q, which is 1 minus P, is 0.4. That's the probability of drawing something that's not a black ball, which in this case would have to be a red ball. So X is a binomial random variable where N equals, let's see, how many are we drawing? We're drawing 4 balls, so N is 4, and we're counting the number of black balls, that's X, and the probability of success, P, is 0.6 every single time. And it's the same every time because we're replacing it. And so this is what the tree looks like. You get a success or failure each time, and so there's always 2 branches. All the green branches go to a success, and all of those have probability P, which in this case is 0.6. All the black branches go to a failure, so they have probability Q, which is 0.4. And here's the binomial distribution. We already know the formula. For the PDF of X, or the probability that X equals some little x, is N choose X, P to the X, Q to the N minus X. So in our particular case, that's PDF of X is 4 choose X, times 0.6 to the X times 0.4 to the 4 minus X. So for example, when X is 0, we get 0.6 to 0, which is 1. We get 0.4 to the 4th, okay, which is just Q to the 4th. 4 choose 0 is 1, so you just get Q to the 4th, which is right here. When X is 1, we get 0.6 times 0.4 to the 3rd power times 4 choose 1. 4 choose 1 is 4, so we get 4PQ cubed, which is here, and so forth. We've looked at this before. Here is the binomial PDF graph and you have, well, at least at 4 decimal places, you have the values of the PDF, or in other words, the probability that x equals 0, 1, 2, 3, or 4 above the bars here. So that's a binomial distribution. Now, let's take almost exactly the same situation. Suppose we have an urn with 10 balls in it. 6 of them are black, 4 are red. And we're going to randomly draw out 4 balls. X is still going to be the number of black balls. So far, this is exactly like the binomial distribution example we just did. But here's the difference. This time when we draw a ball out, we're not going to put it back. So do not replace it. So this is sampling done without replacement, or in other words, no repeats are allowed, where repeats were possible in the binomial case. Now, how does that affect things? Well, we've done trees like this before. Notice still the basic tree looks the same in terms of the structure of it. It's still a success or failure each time. There's still 2 branches each time. There's still 4 layers deep. But the probabilities on the edges are a little bit different. The first one starts the same. The probability of success the first time, we can still call that P. That's the number of, that should say M over N, 6 over 10, which is the number of black balls divided by the total number of balls. So that's 6/10. And the Q is 1 minus that, so that's 4/10. But look what happens here. So we got 6 balls, and we're a black balls to choose out of 10. That's a probability of 6/10. We get a success. If we get a success, the probability the next time is no longer 6/10, though. It's changed. This is a conditional probability. So we see that there are 5 balls that are black out of a total of 9 balls left. So that's 5/9, leaving 4/9 for failure. On the other hand, if we draw a non-black ball the first time, I believe it was the only other possibility was a red, then there are 6 black balls still left, but a total of 9 balls. So that's 6/9 or 2/3. That reduces, and then 1/3 this way, and so forth. So the probabilities change based on what we have there. Now what I have here is I've just multiplied all these numerators and multiplied all the denominators for the numerator and denominator here. I have not reduced these. All of these fractions definitely will reduce. And so here are the probabilities. And there is the graph of the PDF with the probabilities to many places. Now let's see if we can look at what we have here. Well, let's see. Let's look at some of these numbers here. So the orange one, for example, the 480, we're multiplying a 6 times a 4 times a 5 times a 4. Okay. Times a 3, excuse me. And the bottom, we're always multiplying a 10 times 9 times 8 times 7. So the denominator is 10 times 9 times 8 times 7. That's 540. Well, 10 times 9 times 8 times 7 is 10 permute 4. So that's the denominator each time if we don't reduce it. Reduce the fraction. The numerator, well, let's see what we have here. Well, if we have no successes, or if we have all successes, it's 6 times 5 times 4 times 3, which is 6 permute 4. And that only happens one way. If it is here, the orange one, the 480, how do we get that? Well, it's a 6 times 5 times 4 times 4. Okay. That's how we got the 480. If it is the black one, 360, how do we get that? Well, it's a 6 times 5 times 4 times 3. So if you look at just the green ones, that's a 6 times 5 here. Even if the green one is over here, 6 times 5 here. And if we got 2 failures, it's a 4 times a 3 somewhere, either here or here. But of course, there are multiple ones with one success and multiple ones with 2 successes. So this is what it turns out to be. Here's one way we can think of the formula. The probability of each branch with the same value, well, you have your m successes. We're going to choose x of those, and they turn out to be in order. M times m minus 1, and so forth, x of those factors, which is m times p to the x. Then we had n minus m failures, and we have n minus x of those permuted there, and we're dividing by n permute n. Capital N permute little n. But the number of branches with that x value is n choose x. Now if we write these out with factorials, this one is n factorial over n minus x factorial x factorial. This one is m factorial over m minus x factorial. This is n minus m factorial over n minus m minus n minus x factorial. And this is n factorial over little n, big N minus little n factorial. Now I'm going to redistribute around these ones I have that are colored over here on the side. This n factorial, I'm going to put, it's in the numerator here. I can put it in the denominator down here. I can put this x with this first term in here, and this n minus x here. Well, when you do that, this becomes m choose x. This becomes n minus m choose n minus x. And this one becomes n choose n. Big N choose little n. Well, this last formula is actually a better way to think of it. And we've actually looked at this problem before and came up with this formula. So, how do we make sense out of the three parts of this formula? Well, the m choose x is the choose x successes from a total of m successes. So there are x successes in our sample, m successes in the population. So we're choosing x items from a group of m items. Now how many failures does that leave? Well, if there are n, capital N items in the population, and m of them are successes, then n minus m of them are failures. And from those, how many are we choosing? Well, we're choosing a total of n items. X of them are successes. That means there's n minus x failures. So we're choosing the n minus x failures from the n minus m objects. From the n minus m total failures, we're choosing little n minus x failures in our sample. The denominator then is just the total number of objects, n, capital N, choose the little n, and this is how many ways we can just choose n objects totally. Okay, and so these combinations work out pretty nicely like this. Now, without proving it, let me show you this. It turns out that the mean is the expected value of x. It turns out to be little n times big M over little n. But if we call big M over little n, big M over big N, I should say. In other words, the number of successes in the whole population divided by the population size, that's the proportion of successes in the population. Let's call that P. And then the formula is just like a binomial. Mu is n times P. What is P? Well, P is the probability of a success on the very first draw. Now, in a binomial distribution, the probability of a success on any draw is P. But on a binomial, on a hypergeometric, the probability of a success on the second, third, fourth, whatever draw depends on what happened earlier. But for the first one, the probability is P, which is big M over big N. Now this is the formula that it turns out to be for the variance, which reduces to just like a binomial, N times P times Q. But then you have this extra factor. It's capital N minus lowercase n divided by capital N minus 1. So in other words, population size minus sample size over 1 less than the population size. This fraction here is needed in the hypergeometric to take, sometimes that's called a finite sample size correction factor. Okay, and that's to take care of the fact that we're having a finite sample size and we're doing this without replacing. Okay, so don't worry about this kind of stuff here. Worry about this formula right here. All right, so let's do a side-by-side comparison of binomial and hypergeometric distributions. In both cases, lowercase n is the known sample size. And we may or may not know the population size, but it's capital N, the total number of items, the population size. Capital M is the initial number of successes in the population, and X is the unknown number of successes in our sample. Now the difference is basically we're drawing with replacement in the binomial distribution, and we're drawing without replacement in the hypergeometric distribution. The probability of success the first time is always n divided by m. In other words, that's m over n. M over n. So that's capital M over capital N. In other words, the number of successes in the population divided by the number of items in the population, the proportion of successes in the population, that's the probability of success on the first trial. Now, if we do it with replacement, that's the probability of success on every trial, P. So over here, actually, you can base everything ultimately just on the P, so you notice you don't need to know the population size and the initial number of successes. All you really need to know is the probability of success each time. Over here in hypergeometric, however, you do need to know capital N and capital M. You need to know the size of the population and the number of successes in the population. You need to know that. Okay? Q equals 1 minus P in either case. So notice once again, in a hypergeometric distribution, the conditional probability of a success varies. It's dependent on each successive item. But on the binomial case, the probability of success is P, which is constant. It's independent for each item. Now the formula for mu is just n times P in both cases. The formula for sigma is NPQ and square root of that. So the standard deviation is the square root of NPQ. In the hypergeometric, you have NPQ, but then you have this other factor, capital N minus little n over capital N minus 1, and of course square root of all that for the standard deviation. Without the square root, it's the variance, of course, in both cases. So it starts out the same, NPQ here, but it's a little bit extra factor here in the hypergeometric that basically takes care of the without replacement part. Okay, now, if you have this over here, the binomial distribution, we worked out the formula for that earlier. It is the PDF of x, the probability that x equals x, is n, choose x, times p to the x, q to the n minus x. The PDF, or probability that x equals little x here, in the hypergeometric is m, choose x, times n, capital N minus m, choose little n minus x, over capital N, choose little n. So let's go once again, these parts here. This x is how many successes in your sample. You're choosing those from m successes in the population. Then capital N is the population size, so capital N minus capital M, that is the number of successes, number of failures in the population, and the number of failures that we're choosing for our sample is the sample size minus how many were successes. So that's n minus x. So that part chooses the failures. This is choosing the successes. Multiply those together. That gets the numerator. Denominator will be the total ways of choosing a sample of size little n from a population of size capital N, which is that. Now, there are some interesting demonstrations that we can look at online. Here's one of them from the Wolfram Demonstrations Project. You may have heard of Wolfram. They make the program Mathematica, and they also use that to power what's called Wolfram Alpha online. It's a pretty cool place you might go sometime. So here's a situation where we can demonstrate, and if you can see this here, we have some sliders that can vary with this. And notice that we can either choose with replacement, so that's going to be binomial, or without replacement, that's going to be a geometric, hypergeometric series, hypergeometric distribution. And we can control the number of blue balls here and the number of red balls here. And it looks like, well, we see the probability of red and blue here as it's set up here. So probably it would be in red. Looks like red is our success. So both red, that's x is 2. There's the probability. One red is here, and that's x is 1. And neither red, which is x equals 0, is down here. So they've got an illustration of the urn here. Of course, they would be mixed up and randomly drawn out. But we can change this here by changing the total number of blue balls and the number of red balls, and it changes the probabilities. Now notice right now we're putting it with replacement, so when we get red or blue here, red's a success. We see that, well, there's a red blue each time, so there's just a two layer here because we're just drawing 2 balls. And we can see the probabilities here. And all of the probabilities for red are 9/13, and the blues are 4/13 because we have 4 blues, 9 reds. That's 13 balls altogether. Now, okay, so you might try this yourself. What would the tree look like if we did it without replacing? Okay, so actually maybe you want to pause and try that out yourself and see what you get. Okay, so if you paused that and looked at it yourself, hopefully you came up with this tree. Notice that the probabilities the first time are the same, 9/13, 4/13, but after that it varies. So the probability of a red the second time given a red the first time is 8/12, whereas the probability of a red the second time given a blue the first time is 9/12. All 3 of those red probabilities are different. And again, we can experiment by choosing different numbers of red or blue balls.